Hi, everyone. Hello. I first want to thank you all for coming to the 42nd Annual Derby Lecture Series featuring Professor M. Stanley Whittingham. So it's been quite a few years since we've actually had the Derby Lecture Series. It's been postponed due to the pandemic. So we've been actually very honored for the fact that Professor Whittingham originally was planning on coming to the 2020 Derby Lecture Series, and it got pushed back to 2021. He agreed again, and then now the 2022 Derby Lecture Series. So we're very lucky to finally have him here in Louisville for this event. So today is the technical lecture. The general lecture will be tomorrow. It will be in this exact same place. However, it's going to be at 1 o'clock p.m., so we hope to see you all there as well. So I'd like to first say a couple things about CGSA and the Derby Lecture Series themselves. So CGSA is a chemistry graduate student-led organization, and we have been hosting these Derby Lecture Series for about 4 decades now. So we are, so all of the graduate students in CGSA are the ones who organize all of the events and do all of the little things for this weekend to go smoothly. So with these kinds of events, we mostly host Nobel laureates, and because it's a very unique thing for University of Louisville, it allows us as graduate students to interact with these very distinguished and very successful scientists within our field that we normally wouldn't have a chance to interact with. So I'd like to take a moment just to acknowledge all of the graduate students that really helped with the fundraising, who helped throughout the events this week, and who helped putting these events together. So I'd like just to give a hand to all the graduate students who have helped. So I now would like to take some time to discuss Professor Whittingham himself. So he is originally from Nottingham, England. He received his bachelor's, master's, and his PhD from the University of Oxford, and then went to Stanford for a postdoc, and then ended up working at Exxon for about 16 years. So now he's actually a distinguished professor in chemistry. He's a director of both Institute of Materials Research and Materials Science and Engineering program at Binghamton University, State University of New York. He currently serves as the director of the Northeastern Center for Chemical Energy Storage at the U.S. Department of Energy at Binghamton. And he was awarded the Nobel Prize in 2019 alongside Akira Yoshino and Joan B. Goodenough for the development of lithium-ion batteries. So Professor Whittingham has also received quite a few other awards as well. So I'd like to just mention a few of those. So in 2010, he was actually awarded the award for lifetime contributions from the American Chemical Society. And, sorry, I gotta flip the page. And he was awarded the 2018 Turnbull Award from the Material Science Research. So we are very delighted to host all of you for these lectures, and we are really excited to hear the talk from Professor Stanley Whittingham. So let's all give a hand for him.
Thank you very much. You can hear me? This is working okay? Yeah, good. So what I want to do is give you a little bit of background, but also show how important this area is. But first, let me thank the U.S. Department of Energy, who supported me since about, I think, 1993. Those were different days. The students wouldn't understand it, but I was on a JSPS fellowship in Tokyo at the time. My secretary faxed me a message saying, you know, this deadline for this DOE proposals are 3 days away. Are you going to submit something? And I said, yeah, maybe. Let me write it up tonight. So I hand wrote it. Remember, there weren't laptop computers then. I hand wrote it, faxed it back to her. She typed it up and submitted it. And I've had funding ever since from them. So you've got to take the opportunity when it comes up. And for young folks here going after federal funding, don't try Department of Energy unless you know somebody there. It's incredibly difficult to break in, but if you're successful once you're in and you're successful, they will keep you in. So most funding people get from NSF and other places. So I show you a few examples here, and I'll touch on each one of these a little bit later. Grid storage, huge facility in California, 1.6 gigawatt hours. It's been up and running a year or two now. In the middle is a very nice BMW car. I think if you've got about $90,000, you can buy it. It doesn't go as far as a Tesla, but I think it looks nicer somehow. And on the right-hand side is a large facility that's, I think, up and running now in New South Wales and in South Australia. And you can see they had a problem when they started it up. One of the containers caught fire. They sell this as a positive point. It didn't spread to any of the others. And they think it wasn't the battery, but some of the power systems where they had a problem. But this is a sort of thing that I'm going to mention today and why it's so important and why we need lithium batteries. So let me just touch on some of the areas I'm going to discuss for you. I'm going to really talk about the history of the batteries, where we started out, where they're used today, and really how they've really taken over. I'll talk about their impact on getting a cleaner environment, then some of the research opportunities there. I'm not going to touch on some of the areas some of you folks are doing. For example, I won't touch on lithium sulfur. That's half of our Battery 500 program and not the half I'm working on. But that's a huge effort, and an effort which has the greatest potential if we can solve the technical problems. But remember, lithium sulfur was being researched before lithium-ion batteries were discovered. So Argonne and GM were working on those in the 1960s. So going back to the beginning, here's me a few decades ago with single crystals. This is what we used back in those days, and I'll show you what the field is really coming back to single crystals all over again. And then two of the batteries we made back then, a paperweight we gave away to potential customers. You can see this has a solar cell in it, a clock, and our little lithium battery. This particular one still sits on my desk and it's still working. Built about, we think about 1975, 1976. So a well-made lithium battery will last forever. This is the sort of battery you want if you've got a heart pacemaker or something. It'll keep you going. But you will not find batteries as well made as this today, because this was had glass seals in it, it was welded closed, and that's far too expensive. Below that is a battery built for electric vehicles. It's about 6 inches by 4 inches by about an inch thick. We took 3 of these to the EV show in Chicago back in '77, and this turned a motorcycle headlamp on and off all week long with no problems at all. I should say we drove it there, we did not try taking it on the plane. But that's where we stood back in those days. Where do we stand now? This is where we come from, and I'll show you a series of vehicles there. The little car is an Italian car, 2-seater. If any of you have been to Bermuda, you realize you're not allowed to rent cars on Bermuda until 2019, when they allowed tourists to rent electric vehicles. And they just installed these electric vehicles about 2 weeks before my wife and I arrived there for our anniversary. So we rented one of these for 2 days. And they said, if you drive to the other end of the island, make sure you recharge, because they won't have enough power to get you back. So we drove to the other end of the island, went to the recharging station, and they were still building it. So fortunately, on the way back, we found a hotel that had a small recharger, so we recharged the car as we had dinner. But that's a small scale. Next to that are 2 trucks. These are part of the Packard facility, which is part of Peterbilt and a couple of other companies, and this is in the R&D facility north of Seattle. And I had a chance of driving both these around their test tracks. The one in the middle is a 16-wheeler, big truck, and you can see the lithium batteries there. Just like Tesla or anything else, you put your foot down, if that's the right word, it takes off at high speed. And they put about 5 tons of concrete blocks in the back of these for the testing. So I got to test this around their test track and said, please don't go above 60 miles an hour in it. And it very easily gets up to that. The one on the far right is a garbage truck, and that's the ideal use of an electric vehicle because it stop, start, raise, lower, so every time it lowers you get the equivalent of regenerative braking back again. So they're very efficient. The 16-wheeler is in use now in the LA docks. It basically takes the containers from the docks to the distribution centers. So they're trying to clean up the docks. Beneath that is a Mercedes bus. This has an all solid-state battery in it. It was touted as being super safe, but one of these caught fire in last October in Stuttgart, Germany. They think whilst being recharged in the bus garage, burnt down and burnt 12 other buses at the same time. So there's a test, and a different brand of bus with the same solid-state batteries just got banned in Paris about 3 or 4 days ago because 2 of them caught fire whilst in use. So for those of you working on solid-state batteries, please don't sell them as being safer than today's batteries because right now there's no evidence that they really are. So we have to be very careful. The other stuff I'll talk about in a few moments. So let's just look at what the issue is. If we want to clean the climate, we've got to go to renewable energy. We have to get off coal. And I know this is a coal state, but we in New York are very proud. We now generate no power whatsoever from coal. Every coal power plant in New York State has now been closed down. It means we're using quite a lot of gas, but in New York we have a lot of hydropower, we have a fair amount of nuclear and other forms of energy, and they're putting huge wind farms in now. But you can see the issue with coal is coal power plants are now more expensive to build than to put in solar or wind. So even in Texas, and there's a bar chart there, if you can read the fine print, you'll see it, 94% of all new generating capacity in Texas is renewable. And Texas is not exactly known for being, shall we say, a green state. So the economics of the business are now driving it towards renewable. But that means you do need storage, because as we all know, the sun shines when it wants to, and in many parts of the country, the wind doesn't blow at all. So we've got to store that energy, and I'll show you 2 facilities on the right there. The middle one is a facility being built in Texas. They're keeping it fairly secret, and not sure why, being built by Tesla for the grid there. Beneath that is the facility in California. It's about an hour and a half south of San Francisco. Right now, that's at 1.6 gigawatt hours. So that can produce 400 megawatts of power for 4 hours. And they've got planning permission to go to 6 gigawatt hours. So huge facility. It's already 4 times larger than any other facility in the world. And if you read Bloomberg today, it's nowhere near large enough for what California needs. So California's going to be putting much more in. So let me explain why you all have lithium-ion batteries. And I assume there's not a single person in this audience that doesn't have a lithium battery on them at the moment. And they're all lithium-ion batteries. You don't have lithium batteries because of the picture shown here. This is some microscopy work of Russ Keenelly, who was at Exxon back in the 1970s. This is a straight optical picture of plating of lithium in an organic solvent. As electroplating of any metal, you tend to get these dendrites formed. And you can put additives in that might minimize it, but these dendrites go right through the separator and short the cells out. And on the right-hand side, you can see a commercial cell. These were built by Avastor in Canada, then commercialized by AT&T. And these are, I think, in Texas. They had about 6 or 7 of these burnt up within a month of installation. So these were lithium metal anode, polyethylene oxide separator, and I think a vanadium oxide cathode. So again, the lithium dendrites grew through and shorted the cells out. So there really hasn't been any lithium metal batteries in the US since that time. So that's why we all use lithium-ion. If you've got lithium in your batteries, you've got problems. So let's look at what a lithium-ion battery is. And you'll see there's three components here. There's the anode on the left-hand side, the electrolyte in the middle, then the cathode on the right-hand side. Both these electrodes today operate by what we call intercalation reactions. If you get an old dictionary and look up intercalation, it'll talk about putting February 29th into the calendar year every fourth year, then you take it back out and the calendar's back to where it was initially. If you're even more intrigued about it, the Romans really messed up the calendar. So they initially only had 10 months in the year. So they had to intercalate, as they say, 2 extra months, January and August. And it was Caesar who wanted August in because his first name was Augustus. So it's named after him. And I gave a talk at a Rotary Club maybe a month ago, and one of the ladies there gave me a whole book about talking about the intercalation calendar and what the Romans were doing. So intercalation in chemistry to exactly the same way. You're putting some species into crystalline lattice, taking it back out, and the lattice is exactly the same way before and after. And that's why lithium-ion batteries, you can recharge them thousands of times. And what you look for is, are we damaging the lattice whilst we're doing that? So a lot of structural work, particularly at national labs, looking very closely at how those atoms are. So the anode, today we use graphite, and I show you graphite here, the sheets of graphite with little green atoms in between them. On the right-hand side, another layered structure, and I'll show you some of the examples of that in a moment. But again, so we have both layered structures, then in between we have an organic solvent with a salt in it. Typically this is LiPF6, although some of the latest ones are using LiFSI in it as the salt. It is that burns. Once that starts burning, then the graphite starts burning. What can initiate it are the oxides, and I'll get into why they initiate it in a moment. So this is a typical picture. How did things progress over time? So at Exxon, which was ESSO when I joined them, we started looking at batteries because we were studying superconductors. And my job as a chemist was to make these superconductors, and we made them at room temperature by intercalation reactions. And we found out in some of these intercalation reactions there was a huge amount of energy involved. So everything got hot, so we said, maybe we can store this energy. So that's when we switched to looking at them. Superconductivity materials were tantalum disulfide, very heavy. Somebody was asking about what can you intercalate in these materials. We're looking at long chain amines, C24, then the amine group at the end of it. So we could spread them apart, change the electron density, and that changed their superconductivity. As soon as we got interested in the energy, we switched from tantalum to titanium for obvious reasons. Much lighter. Now showing you in a minute, titanium has some other big positive parameters. So we looked at the lithium. We early on saw dendrites, so we switched to a lithium aluminum alloy. So if you do any semiconductor work, you'll know from the semiconductor people, they'll tell you we don't want lithium anywhere near our chips. Lithium reacts with everything. So lithium will react with aluminum at room temperature with no problem at all, forming the one-to-one alloy. So we worked with that material and used that in most of our commercial batteries for safety. It's good for 10, 20 cycles, but it crumbles very quickly. So Akira Yoshino then said we could use graphite, and he was working on some cokes at his carbon company and got that to work. The problem with graphite, you need 72 grams of graphite to store 7 grams of lithium. So huge wastage of weight, and in a lithium-ion battery, half the volume of the battery is that graphite anode. So the goal is to take that out and to replace it, ideally if we can, going back to pure lithium, But in the interim, we're looking at things like silicon and tin. Both silicon and tin react with more than 4 lithium ions. So on a volumetric basis, they're just as good as pure lithium. But when you put the lithium into these materials, they expand by 300%. Means they're very reactive, so they react with the solvents and give us other problems. On the other electrode, so intercalation compounds, we worked on titanium disulfide. John Goodenough, who was then at Oxford in England, was looking at magnetic behavior of cobalt oxides, particularly lithium cobalt oxide, and said, this has the same structure as titanium disulfide. I'm going to try it. Now, none of us at Exxon or Bell Labs, or I should say Exxon and Bell Labs, were competing in this area. Who could get the publication out the quickest in those days? We know none of us looked at cobalt. You can't make cobalt-4. All the chemists are taught cobalt-4 doesn't exist. John Goodenough, being a physicist, said he's going to try it. And I should say he was head of the inorganic chemistry department at Oxford at the time. So he tried it, and that worked well. That's what's in all your calculators, your watches. It still has the highest energy density per unit volume. Okay. But cobalt's too expensive. Most of it comes from the Congo, and about half of that involves child labor. So there's a big emphasis to get that out, and it's being replaced by nickel and manganese. So you'll see that this NMC just means nickel, manganese, cobalt cathode. And that's really where most of the effort is today. John also found out that LFP, lithium iron phosphate, would also take in lithium in and out. But you're carrying a phosphate group, so that again reduces your energy. So what we've been looking at is if you reduce the energy and you want to use a phosphate, phosphate is much more stable, so it's safer. You've got to try to put in 2 lithium ions. So I'll show at the end where we're managing to use vanadium, where you can go from vanadium 3 to vanadium 5 in a reversible manner. So why is titanium disulfide so interesting? First, from anybody who does phase diagrams, it's a single phase all the way from 0 lithium to 1 lithium. The lithium can go in there, just slowly expands it. So you don't have to nucleate a new phase. Second, it's a metallic conductor. And the physicists here will grumble, it's really a semi-metal as they describe it. For all practical purposes, it's a metallic conductor. And remember, in a battery, putting lithium ions in and out, you're also putting electrons in and out. So the cathode has to be conductive. Normally what you do is mix carbon black or something with it. With this material, you didn't need to do any of that. Okay. So it reacts very well. I show you a plot here on the left-hand side. This is a lithium TiS2 cell from way back when, running at 10 milliamps a square centimeter. Extremely thick electrodes, far thicker than would ever dare use today. And the charge and discharge plots are separated just by the resistance of the electrolyte there. And it's nice smooth curve, which means it's like a gas gauge in your car. So by measuring the voltage, you know exactly how much energy you've still got left there. We'll show a little bit later. There are some materials which are flat. You have no idea whether you're 90% full or 90% empty. Okay. So this has some advantages. In the middle, I show you the example of sodium. Sodium goes in just as easily, but now sodium is bigger. So it has to get those layers and pull them apart to go in. That takes energy. So now we see we've got 2 or 3 separate phases formed depending on the sodium concentration, and you see the voltage drops dramatically. So there's very little interest in these particular sulfide materials. For sodium batteries, for layered oxides, there's still some interest. And on the right-hand side, I'll show you the picture for a magnesium battery, and this is work by the Canadian group. And the thing what they found out is it's a good metallic conductor. That means the charge on the magnesium is shielded. It's a soft lattice, so the magnesium ions can diffuse in and out. But again, look closely at the numbers. This is operated at 60 degrees centigrade compared with room temperature. and it's operating at 0.04 milliamps per square centimeter, not 10. And the voltage is about 1 volt lower than the lithium batteries. So maybe 10 years ago, there's a lot of push. Magnesium's going to be the answer. We can get 2 electrons in. But it wasn't until Anton van der Ven at Santa Barbara did theoretical calculations of the voltage and said the voltage is going to be about a volt lower, that people started looking at it. And the Canadian work was after he did the calculations, and it was within 50 millivolts of what he had calculated. So you can see that commercially there's very little interest in magnesium anymore. The voltage is too low. The magnesium ion is too polarizing, so it won't move fast. There's still interest in calcium. It's bigger. It should move faster, but no one knows how to plate out calcium metal at the moment, so that's the challenge there. So that's where we stood with TiS2, but really all the interest is in the oxides and then the other materials, and the interest is, there are lithium batteries everywhere today. Do we need more research? The answer is yes. If you look in that red oval there, that gives you the percentage of the theoretical capacity on a volumetric basis we actually get out of a commercial cell. So you can see it goes from about 11% to 25%. So there's a huge gap there for improvement. On the far right is the same number for on a weight basis. They're about 25%. So I'm part of the Battery 500 consortium. The 500 means they want to get to 500 watt-hours per kilogram. Today we're about 250. So the goal is to get that number from 25% to 50%. We're up to about 350, 400 at the moment, and we're just beginning our second 5-year period, so we expect to get close to 500. The Battery 500 consortium has these NMCs as half the effort, the other half is lithium sulfur. We should have no difficulty at all in getting to 500 with lithium sulfur. The question is how many cycles can we get out at 500? Is it more than what you can count on your fingers, which is one of the challenges today. So that's what a lot of our effort is. It means we've got to get most of the graphite out. We've got to get more lithium into these materials. And ideally, we've got to make the electrodes thicker. Remember, every battery, you need a current collector to take the electrons in and out. You need a separator in between. So we can make the electrodes, say, double the thickness. We can take half of those current collectors, half those separators out. But they've got to be sufficiently conductive, both for electrons and lithium ions. So we're working on that. So let me talk briefly about what we're trying to do. So on these NMCs, nickel, manganese, cobalt, what we want to do is get the highest energy density we can at the lowest cost. If you look at this plot here, this is a plot from folks in South Korea. The vertical axis is the thermal stability. So if we charge these materials, let's say we take 70% of the lithium out, then we heat them up in the DSC. At some point, they lose oxygen. So it's what I said originally about John's work at Oxford. All these oxides, when the lithium's out, the +4 oxidation state, the metastable, in principle, they should evolve oxygen at room temperature. But it's kinetics. So this is just telling you what temperature these materials are going to lose oxygen. And you can see from the axis at the bottom, we want high energy density, which means we want to be at the right-hand side. If we're at the right-hand side, then we have the lowest thermal stability. Now, we hope we never take these batteries to these temperatures, but this measure of thermal stability is a direct measure of how reactive they are with the organic solvents. So the higher the thermal stability, the less reactive they are. So in the essence, the higher the nickel content, the more reactive they are. But we want high nickel for 2 reasons. It gives us higher energy. It takes out the cobalt. So today in most batteries, EVs, grid storage, we've gone from what we call 333. This means 33% nickel, 33% manganese, 33% cobalt, up to 80% nickel, 10% manganese, and 10% cobalt. that has cut the cost of these cathodes down by more than 50%, because almost all the cost is in the cobalt. So we've done that. Tesla uses what they call NCA, which is nickel, cobalt, and aluminum, and they're now up to 90% nickel in their cells. Okay. So we have this issue of, do you want more energy or do you want more safety? And we all know the answer. We want both of them together. So a lot of our effort, my particular team on the battery 500, our job is to look at the chemistry, all the side reactions that can occur, and can we eliminate those as we push these to their limits. And if we can do that, then we can have, as they say, our cake and eat it too. So let's just look at what we're actually doing in this project. I said this project's been going on now. We finished our first 5 years last September. If you look at the plot here, the data on the left-hand side is 2017. You can see we got 50 cycles out of this material at 300 watt-hours per kilogram. Then we went up to 250 cycles a year later. The following year, we increased the energy density to 350 and got the same number of cycles. And today we're, I'm told, close to 1,000 cycles at 350. We have, in fact, got quite a lot of cycles at 400. We're not allowed to talk about that, though. We can, when we publish it, then we can talk, but according to the federal government, above 350 is export-controlled information. Okay? So at some point, we'll publish all that. But this data, we provide the materials. Then Jay Xiao, my ex-PhD students at Pacific North National Lab, makes the cells, and I'll show you a typical cell. Here, these are pouch cells. To get the energy out, we actually weigh the cells, measure the volume by immersion in liquids. So these are real numbers, not the fake numbers. Be very wary to read the literature. They'll give energy densities just for the active material, or in fine print in some companies. Energy density when extrapolated to large cells. But the numbers I show you here are real cells, and the cells are in fact tested at Idaho National Lab. So one place makes the material, another one makes the cells, and the third place does the testing. So it's totally independent. There's no one group kind of saying, hey, I've got the greatest thing. So we work very much as a team. And I should emphasize the materials we use commercially today are what we call meatballs. You can see why, looking at that. Now, the primary particles are about 100 nanometers or so. The secondary large particles are anywhere from 5 to 20 microns in size. And these pack well. They're very good at making batteries, but I'll show you in a moment, they have some major problems. And the major problem really is push them to the limit. I said we're intercalating in these materials. But as you intercalate, clearly the lattice is expanding. You're putting something in there. So the lattice expands, and if we got one crystallite this way, the next one this way, as they expand, eventually the interfaces crack. And then that cracks the meatballs. We've got fresh surface in there, which then reacts with the electrolyte, making them more resistive. And what I didn't mention, all lithium-ion batteries, when they're manufactured, they are cycled between 3 and 5 times at the manufacturing plant to form a protective, what we call SEI layer on the surface. Once that's done, the gas is let out, fresh electrolytes put in. But if these things crack in use, then you're making fresh surface, reacts with the electrolyte, and that raises the resistance, but more importantly, it uses the electrolyte up. Lithium-ion batteries, for the most part, are like your alkaline cells. If you open them up, nothing should drip out. Lithium-ion batteries the same way. It's minimum amount of electrolyte in there to give you the highest energy density. So Jeff Dahn and the Koreans did some studies on these materials, and Jeff Dahn found out the lattice volume didn't change very much until you took out more than 70% of lithium. And you can see how it falls off the cliff on the left-hand side over here. That's where the cracking starts. And he says if you go above that limit, you're not going to get long cycle life. The Koreans did similar studies. They looked at capacity loss, and you can see the same plot. As soon as we go to high nickel, we push it to high capacity, then we have capacity loss. So our goal is to say, can we eliminate this? Can we go to high capacity and not have this capacity loss? And what we ideally would like to do is use all lithium in the material so we don't have to stress them so much. But I'll come back to these meatballs in a moment. But thing we have been looking at, we're diffusing these lithium ions between these sheets. What we find out, we can take the lithium out. When we try to put it back in, we never get the last 10% in at a reasonable rate. So on the very first cycle, you're losing somewhere between 10 and 15% of your capacity. That capacity is at about 3.5 volts, where these cells are very, very stable. So we have to use that capacity, rather than pushing them up to, say, 4.5, 4.6 volts, where the lattice changes much more. So we've been looking at what's the cause of this? Can we solve it? Can we recover this and keep it in use? Being a kind of materials person, chemistry person, the other thing we looked at is not going back in, is this diffusion controlled? And so we measure diffusion coefficients just using standard electrochemical type techniques. And you see here, the solid points is the lithium going in. You can see it falls off the cliff after about 70% of the lithium going in. It's exactly the same as in this lecture hall. Okay, it's full about now. If some people come in and want seats, invariably the empty seats in the middle. So everybody has to move. But the actual diffusion mechanism here is a divergency. So you need, in fact, 2 vacancies. That means you need 2 seats empty for another person to move in. That's why it falls off the cliff so fast. The open circles is charging, taking the lithium out. You can see there's no problem there. It's exactly the same as here. When I stop talking, you can all go out and no one will really block anybody from getting out of here. So the issue is really just on inserting the lithium in. So we've been looking at, can we modify the materials? But first, to double check that this wasn't really the case, we looked at these materials at 2 different temperatures, room temperature and 45 degrees, and at a series of different charging voltages. Clearly, the higher the voltage we go to, the more lithium we take out, so the more capacity we get. Then when we discharge it, what we do is keep within voltage regimes. We discharge to 2.8 volts. To see where there's kinetic control, we then just held it at 2.8 volts. And you can see the flat plateau, I think this bit here. If you hold it there, you're getting more and more lithium in. At 45 degrees, you're getting it essentially all back in. So this is clearly diffusion controlled. So we just have to solve really a diffusion issue. Can we modify the lattice so we can go back in? And there's sufficient evidence we should be able to do that. If we look at the pure lithium cobalt oxide, there's no first cycle losses, we call it. You can see this on the right-hand side here. At the top, we have our 80% nickel, NMC. In this case, we just charged it up to a fixed capacity, then discharged it at 2 temperatures. And you can see, I think here, the red one is higher temperature, and you can see it almost all goes back in. So this is 45. So we don't have an issue here. Cobalt oxide, you don't have to go to higher temperatures, no first cycle loss period. So we're saying we should be able to take our layered oxide, modify it by, say, substitution or something, convert it to make it look more like lithium cobalt oxide. And that's what we've been trying to do for the last few years. And what we've been doing, and we looked at both aluminum to do this, and it works to some extent, but we've been particularly looking at niobium. Lithium niobium oxides are well-known ionic conductors, so we know lithium can diffuse through it, so we make a film on the surface. Lithium can still get in and out. So what we did was treat our meatballs with a lithium niobium ethoxide solution and fire it up at different temperatures. At the lowest temperature, we form a nice coating on the surface. Higher temperatures, it goes right into the lattice. What surprised us, the surface coating isn't a lithium niobium oxide. Turns out it's a lithium niobium manganese oxide. So some of the manganese goes, some of the niobium goes into the lattice, ejects some of the manganese, which then forms this protective coating. And I think you can see here, we've got back about 50% of this loss. We think if we optimize this, we can probably get all of it back. So that'll be a big saving. But it's these little things that can get us, say, from 250 to 300 to 350 to 400 watt hours per kilogram in commercial batteries. And I should have said that data we showed a few slides ago did not use a standard electrolyte. It did not use a graphitic carbon. It used pure lithium metal. So we had to learn how to plate lithium metal out. And what the researchers at Pacific Northwest National Lab, in fact, did, I'm not sure they did it knowingly at the time. They basically went back and used the old Exxon electrolyte that we used when we used lithium metal. So ether-based solvents, and they used LiFSI as the salt, which wasn't available back in those days. And that seems to plate lithium fairly effectively. We're still trying to work out how good the lithium plating is, because we want very smooth lithium, not mossy lithium, which can get formed in many cases. But I said, the interest these days is, are meatballs the way to go if we're going to stress these electrodes? So if we go back to square one, back to the 1970s, TIS2, we used these huge crystals. No, we could make these a centimeter long. Clearly in battery use, we didn't use them that big, but they were hundreds of microns, even for battery use. Sony, when they commercialized lithium cobalt oxide, they tried to make the lithium cobalt oxide crystals as large as they could for safety. The less surface area, the less side reactions. Then for energy density, the commercial folks all went to meatballs. And now there's a track back. And in this bottom corner here, these are crystals made by Jeff Dahn's group. He's the first one to really start pushing this, saying if we have crystals, they're free to expand and contract. And we all worry that means you get less material into the electrode. It turns out we can get just as much in, so there's no penalty there. But the big saving there, less surface area, less side reactions. These batteries in principle should last a long time. And he coined the term million-mile batteries. Now, I don't think anybody in this room is going to drive 1,000,000 miles in their EV. But the reason you want 1,000,000 miles is when the car is not actually moving, it can be tethered to the grid. So as soon as you park it, you plug it in, so your utility can take energy out or put energy in and smooth the grid there without having to have separate grid batteries as well. And if you have a power outage at your home, you can keep your home going off your car battery. But to do that, you need a much better battery than we have today. That's why you need something that will last 1,000,000 miles. And my colleagues at Pacific Northwest National Lab have done more in-depth studies of single crystals, and they say you want single crystals between about 2 microns and 4 microns in size. They pack best, and above that size they will crack, below that size they will not. So they're optimizing that. Just let me switch to a few other compounds for the last few minutes. I show you top there a list of the materials. Exxon worked on titanium disulfide. Most people have forgotten that Molly Energy in Canada worked on molybdenum disulfide for a decade or more. Molybdenum disulfide is molybdenite. It's naturally occurring in British Columbia, so they're going to dig it up and use it. And they built batteries for maybe 10 years using pure lithium metal anode. They were used in the black boxes of some planes until they almost brought down 3 planes. So that's when they stopped using those. and they got taken over by a Taiwanese company, and they switched to graphitic anodes in there. But the interest then moved away from the layered oxides. I say interest, the research interest. Us folks wanted to do something different, to look at the phosphates, and I show you the structure here of lithium iron phosphate, a tunnel structure, so much more stable. But I said it carries phosphate groups with it, means it stores less energy. But the issue here, this is what we call a two-phase reaction. So you've got iron phosphate, lithium iron phosphate, and if you all know your phase rule, that means you've got two phases all the way, a single voltage all the way. So how do you tell whether it's 20% empty or 80% empty? Read Tesla's manual, because they're putting this in some of the Model 3s these days, and it says whenever you get home, plug them in. So it's always at 100%. So there's in fact no easy way, unless you have a kilometer that actually measures how much you're taking out. So we looked at this and said, no, this is great, it's stable, it should be used in grid storage. It is a little bit, but nowhere near as much. No nickel, no cobalt, should be very low cost. Iron is free, phosphates, tons of it around. So we said, let's see if we can increase the energy density by putting more than one lithium in. And there was some prior work we had done and others had done. We initially looked at the layered sulfides and selenides, and it turns out vanadium diselenide, you can put two lithiums in. You can see the red, the plot at the bottom here, this one here. Very reversible, no issues at all, except the voltage is too low. Mike Thackeray at Argonne looked at the layered oxides, and again, you can put two lithiums in, but the second lithium's at such a low voltage to be of no interest at all. But what we found out with this vanadium phosphate, VOPO4, and it's the one in the red here, we can put one lithium in at about 4 volts and another one in at 2.5 volts. And we published this particular data 15 or so years ago, and then we got grabbed on our knuckles by Dewey, why are you working on vanadium? Isn't that nasty stuff? And all the rest of it. So we stopped working on it for a while, then maybe 5 years later we got told, why aren't you working on vanadium? So in federal funding, you've got to be flexible and go as the winds blow. So we looked on that, and clearly, if it wasn't successful, I wouldn't be talking about it. But this is was part of our EFRC effort. So we looked at this material and said, can you in fact intercalate 2 ions into a crystalline lattice without destroying that lattice? And we indeed showed proof of principle we could. This was a team effort. So we had experimentalists, we had theoreticians, and then we had all our national lab, big instrument people working on it. And here's one of my students and one of Claire Gray's students from Cambridge in England, who collected one of the prizes from the Department of Energy, showing that we had succeeded in this, and this is one of the undersecretaries there. So what is this material? It's a nice tunnel structure. It's better than lithium iron phosphate. Lithium iron phosphate is one-dimensional tunnels. These are 3-dimensionals. And you can see the lattice there. The challenge was, can we make this material in a form that's electrochemically active? Remember, phosphates are inherently great insulators, so you can't get electrons in and out. So we had to make them small enough and get them in. And after many attempts and many years of a student frustration, I think, we made these by what we call solvothermal hydrothermal techniques. You dissolve all the materials into a pot. We used alcohol as the main reagent with a trace of water to stop over-reduction. And we made this nice open lattice here full of protons. We can take these protons out just by gently heating it, or we can put it in an electrochemical cell and pump all the protons out. So we can show that protons are also reversible. When we make these materials, no, I'm a solid state chemist. We want to understand them. We want nice, clean materials. So we use a fair number of what we say straight chemical techniques rather than electrochemical to make some of our materials. So if you use electrochemistry, you've got binders in there, you've got carbon in there, it messes up structural studies. What we developed at Exxon was a series of chemical reagents, the primary one being N-butyl lithium. When that reacts with any of these materials, the side products are mostly octane, butene, and butane. So nothing messy in there, so we get nice structures out. So this is what we measured by synchrotron studies. We could actually get lattice parameters out. And this was a huge plus because we found that it expanded by, say there, about 8%, less than graphite when you put 2 lithiums in. If it only expands that much, it should be stable. So we measured both these structures. There are similar reagents you can use if you make a lithiated compound to take the lithium out. So this is the material we made, little cuboids, about 100 to 200 nanometers in size. Very, very uniform. And on the right-hand side is the cycling data here. As a chemist, now, if you're going to put 2 lithiums in, you're going over 2 redox couples, so you should have 2 different voltages. So the vanadium 5 to vanadium 4 is at about 4 volts. The vanadium 4 to vanadium 3 is at 2.5 volts. The main point to notice here, the black curve the black curve here is the first cycle. The purple one is the 50th. The 50th cycle is in fact better than the first cycle. So there's less loss there. So this was really proof of concept it would work. Like everything else, no. We got proof of concept, it doesn't mean it's going to be viable commercially. So one of the things we do with this is look at kinetics. How fast can we get these reactions to go? What are the reaction mechanisms? And we found a number of issues. First, if you look at the top one here, you'll see that the capacity falls off very fast as we increase the rate of reaction. So that's this one here. So 0 to 50 means it takes 50 hours. C is 1 hour. So you can see here's our capacity just falling off extremely fast. It is not a high rate material. And our structural studies said we have VOPO4 plus LiVOPO4, so we have a 2-phase reaction. So right now we're trying to change that. In contrast, vanadium 4 to vanadium 3, that's this curve in here. So to make this, we charge down here, put 2 lithiums in, then just cycle at a lower voltage. You can see in here there's really no difference from 50 hour to 1 hour. Extremely high rate. The difference is in here, again, just resistance of the electrolyte. So we've got extremely high rate for that low voltage region, and that's a single phase reaction. You can see these bumps in there, that's where the lithiums are trying to order themselves. So we have to solve the rate problem. You'll also notice in this region here, this is the amount of charge you're putting in the black. The red is how much we're taking out. We're taking out the theoretical on every count, so we're putting more charge in. So our vanadium phosphate is in fact reacting with the electrolyte. It's a very good electrocatalyst. And if you work with the oil companies, you may know that vanadium phosphates are commercial oxidation catalysts. So it shouldn't be a surprise they're actually reacting with our materials and with our electrolytes and slowly wrecking it. But it does not wreck the material itself. So those are the challenges we're working on right now. So what are some of my conclusions? We're going to be working on it, intercalations probably for the next 5 to 10 years. I'm part of a DOE Liebridge effort right now, is trying to get industrial input to where the government should put their money in so we can get a domestic battery manufacturing going. And all the evidence is there's nothing that's going to knock the present intercalation batteries out of business. And you can see we invented the cells in the 1970s. The first commercial success, not the first commercial activity, was Sony in about 1991. and this is why US companies don't like investing. A patent lasts 17 years. So it got commercialized successfully just about the time when all the patents expired. And this it tends to be invariably the case. So any new technology will take at least 5 years. And the issue now is lithium-ion, they're making billions of these every year, so the manufacturing has really come down. Anything else is going to have a niche market to begin with where they can charge more for it. We've got to make lithium metal work, though there's clearly challenges there at the moment. We've got to have new manufacturing techniques, and this is where people aren't doing all that much. It takes 60 to 80 kilowatts hours of energy to make a 1 kilowatt hour lithium-ion battery. That's from the mine to the finished product. That's not sustainable. We have to change that. What that means is we can't send every atom in the lithium-ion battery through China before it gets to us. So most of the processing of the materials are in China, partly because there are not the environmental regulations there, and partly because of lower costs. That is slowly going to change, and what we're pushing for is every region, or if you like to call that the continent, needs their own supply chain, their own battery manufacturing. Europe's, I think, spending several billion euros to do that, with the manufacturing and mining occurring in Scandinavia with clean hydropower, than the batteries being made in Germany or Poland. North America has to do the same thing. But we also need to come up with new clean mining manufacturing methods, not carbothermal. We got to know, can we use electrochemistry in some means so we have clean energy and not generate all that CO2? I've talked about this Mercedes bus earlier. This was very promising until last October when it started having problems. So until those problems are, we fully understand them, the battery company will not tell us what's going on. They say they're not allowed to talk until the Germans have finished their studies. But it's probably the battery, but it may be electronics or something else. The other area we have to put more effort in, and this is again mostly for chemists, is clean recycling technologies. Now we can't afford to throw all this cobalt into the waste dumps. There's probably some garbage dumps around this town that have more cobalt in them than the mines in Congo, because people toss all their used devices into the garbage. And really we need better chemistry and materials and understand it to really advance. What I want to do is just finish on some comments mostly for the students, based on the speech I gave in Stockholm at the banquet. And we really tried to give 3 messages there. The most exciting science or engineering is at the boundaries of the disciplines. It's not within the disciplines themselves. So a lot of you are chemists. The exciting areas in chemistry is either between chemistry and biology, which means medicine, or it's between chemistry and engineering or materials, which is then new materials and properties like that. But this in perspective. Now, I'm a chemist by training. John Goodenough was a physicist, and Akira Yoshino was an engineer, so it took the 3 of us working to get this done. Same thing, no, I don't need to tell any chemistry department there. There's probably no chemistry department I know in this country that has more, shall we say, American-born graduate students than they have foreign-born graduate students. So you're all used to working internationally, but no, essentially there are no boundaries. You have to work across international boundaries these days, whether you like it or not. So again, put in perspective, no. I was British, I made my invention in the United States. John Goodenough was in fact born in Germany of American parents. He's American, but he made his inventions in England at Oxford. And Akira Yoshino is Japanese, and he made his in Japan in industry. So again, it went across 3 different continents. Whether it would have worked within one continent, I'm not sure. I don't think so. And as the Nobel folks said, you wouldn't have all your toys, your batteries, your watches, or laptop computers without the lithium-ion batteries. So lithium-ion batteries really enabled the electronics revolution. It enabled us to know exactly what's happening in every part of the world instantly. Things didn't have to get shipped. I needn't go into the other things here. So if science is international, it means we need to understand the cultures of other people. That's why you can't just study chemistry or physics. You've got to understand how others think. Now, even Europeans and Americans don't think the same way. They have different priorities. And none of us think the same way as Asians. So no, we have to understand these other cultures, and I put it in perspective. I spent 3 months in Japan on a JSPS fellowship back in '93. And my host there and I had to concoct systems when I gave lectures to force the students to answer questions. The students in Japan are taught, never ask anybody senior than yourself a question. That's considered rude. So I would give a talk, then he would start questioning me, then he'd point at various students in the group, now your turn, now your turn. It's the only way we could get them involved. China is not the same. Chinese will stand up and without any concern, but in those days there wasn't really no Chinese science. So we have to understand the culture, and the key thing of all of you in this audience who are mostly technical folks, you have to emphasize that facts do matter. We go through administration in this country where I think facts and science gets in the way of their beliefs. We have to keep, pushing back, and something we're pushing now with DOE and some of these federal initiatives. We need a federal plan that goes across administration so it doesn't change every 2 or 4 years, because this country will never get ahead if we do that. And I will stop there and answer any questions you might have. Thank you very much.
If you have any questions, please raise your hand.
Thank you so much for coming and giving this wonderful lecture. In 2-electron system, the last material that you mentioned, you're not able to use both because you have such a huge voltage drop between the two.
The answer
Either
is
use
yeah.
one or two.
No, we can use both. For most applications, remember a car works at, I don't know, depending on the company, 600 volts, 800 volts. So it's all DC conversion. So I was worried about this, and an electrical engineer said, stop worrying. The more they're apart, the more it will cost for DC conversion. So we'd like it closer. But we can live with that if it gets us more energy. And some of the high manganese, high lithium compounds I didn't talk about, they go from about 4.3 volts down to about 2 volts. Very slopey all the way, and the same thing there, they'll use DC conversion to solve that problem. In the end, it's a trade-off between dollars and energy.
Excuse me. So it was a really interesting slide where you showed, I guess, micrographs of meatballs and the crystals.
Right.
So the structural studies of meatballs must be quite challenging, I would guess. Could you give us some idea what techniques you use? And also the crystals, they didn't look like microcrystals to me. They were sort of rounded off on the edge. When I look at microcrystals, they look like little diamonds and things like that. So what's going on there?
The rounding off because they're dissolution crystallization process. So they're continually growing on the surface, we think.
But they diffract like single crystals?
Yes.
Okay.
Yeah, if we look at them in a powder diffractometer, we only see them.
Okay.
And the meatballs, there's lots of people been looking at those in SEMs, TEMs, slicing them up to look at what's inside them. And
I see, okay.
Hi, so that was a super interesting talk. I'm a PhD here that works on solid state batteries. So I have like 20 questions that I would like to ask you, but I'll just keep it down to a couple. So I'm just curious on what you think about solid batteries in general and where that might lead to. And then also you said that you began with the lithium anode in like 1970, and now we're trying to circle back to that. So I'm just curious on like why specifically is that process happening now? Yeah.
That process is happening now because of the hope that we can get solid-state batteries to work. So we got a solid electrolyte in there. It was thought that dendrites would have a greater difficulty shorting, and if they did short, it would be a very small short and they would melt themselves out. These fires in Paris and Germany saying maybe that's not the case, but it may be the case if we're using inorganic solid electrolytes. So that, no, the PO will burn just like the organic. But the issue, as soon as you use a ceramic electrolyte, you've got a ceramic electrolyte, you've got a ceramic NMC cathode. How do you keep that interface not broken? Because clearly the cathode is going to expand even just by 5%, it will break the interface. So whenever you hear somebody give a talk about all solid-state batteries, always ask them the question, how many drops of liquid do you put in there? Don't ask them whether they do or not.
That's supposed to be a secret.
No. Certainly QuantumScape adds it. Most of the other companies I've talked to, if they're using ceramics, the garnets, they're adding a few drops of liquid on that side. And no, you have Samsung saying they've got these solid-state cells working, but they're putting, what, thousands of atmospheres pressure on there, which is totally unrealistic. So there is an issue at the solid electrolyte lithium interface, keeping that in good contact. My suspicion is we're going to have dual solid electrolytes, one that's stable to the anode, one that's stable to the cathode. But no, if we really want to go with lithium and want to get the energy density up, the goal is to go solid state. And I expect that you see the first ones in things like your watches, the smaller devices. You're not going to see it necessarily in cars, even though these buses had it in there, just because OEMs are not going to be comfortable. No, one fire and their business is gone. So they're going to want to test out in small systems first. But solid state, no, 10 years from now, I think we may have something commercially available, but let me be completely open to you. I'm an advisor to QuantumScape.
Stan, right. Thank you for coming, Stan. And you showed a graph where you showed the stability that Korean group. I think the nickel compounds were the most stable. Do you know what causes that? What is the reason behind that trend that you're seeing?
No, the nickel compounds are the least stable.
Least stable, sorry, yes.
Because nickel 4 is less stable than, say, manganese 4 or cobalt 4. So it wants to evolve oxygen, and if you had the right catalyst, it would evolve oxygen at room temperature, I'm sure. No one's actually measured the effective partial pressure of oxygen in these materials, but my betting is it's above an atmosphere at room temperature. So it's a fire waiting to happen, if that's the way of putting it.
Okay, so we're gonna wrap up the technical lecture, so let's give another round of applause for our speaker. I'd also like to mention that we will have a meet and greet for the graduate students at 2 p.m. in the BAB room 218. So if any other graduate students want some more one-on-one time with our guest, please feel free to come to that. So we look forward to seeing you all tomorrow as well. Have a good day.